This video will discuss heat pumps and their coefficient of performance. So a heat pump is a device that moves energy from one location to another, where the movement is from the cold region to the warmer region. So this is not spontaneous movement of energy. The laws of thermodynamics say that will never happen, that spontaneously energy will move from the cold area to the warmer area. But we can create heat pumps that do this. They're heat pumps for homes that can warm the home in the winter months and cool the home in the summer months with the same piece of equipment. And you possibly have a refrigerator in your home, and that device takes energy from the cold region inside the refrigerator and moves it to the room that is at a higher temperature. At least I hope your refrigerator has a lower temperature inside than the room temperature. So let's discuss the diagrams here for the heat engine and a little bit on the PV diagram. But the situation for the heat engine is reversed for the heat pump. For a heat engine, energy was leaving the high temperature reservoir, being captured partially by the engine and delivering some useful work, and then there was energy rejected to the cold reservoir. For the heat pump, work is put into the mechanism. So you hook this up to electrical power supply. Electrical energy will make the engine do its job, and in the process, energy is taken from the cold reservoir and moved to the high temperature reservoir. Now you might ask, why would we want to do this? Why not just put work directly into the high temperature reservoir? Well, it turns out that the heat pump can deliver more energy to the high temperature reservoir than the work energy that is used in the process. So it's kind of a multiplier. And we'll talk about the coefficient of performance, which is the ratio of QH divided by W. So you can have multiple times the energy delivered to the inside of the house compared to what is required to run the device. So here's our PV diagram. Where is the net work illustrated on this diagram? And you should say inside the more heavily purple colored area. And is this work a positive or a negative? Now, we're not going to do the calculation, but take a look here. We have a compression on this isotherm. We're going from higher volume here to a lower volume here. The gas is being compressed. That work is a negative number. And down here we have a positive number underneath the lines here as the volume increases. So a big negative work number, a smaller positive work number, and our net work is a negative value. And look at the energies as well here. We have Q delivered to the room, the Q sub H here, occurring at this higher pressure situation, higher temperatures in the PV diagram. And here we have a situation where the temperature is lower, and we have the energy extracted from the low temperature reservoir. So that's kind of illustrated. I kind of like the diagram on the left better. It gives you a feel for what's going on. We put energy into the heat pump. We move energy from the cold reservoir to the hotter reservoir. As far as a little bit of the details of what's happening inside, there is a loop here, and the working fluid moves around this loop. There's electrical pumps that do the job here. So if we compress this, we put work in, we're going to make this temperature hotter, and here we now deliver to the inside of the house. This condenser temperature is higher than the room temperature in the house, so energy will naturally move from this condenser mechanism into the house. We come through an expansion valve, and when the working material here expands, it cools off. It has a temperature now out in the outside that is lower than the air temperature outside, or if it's a heat pump that uses groundwater, then we have a temperature here that's lower than the groundwater temperature. So energy is going to come in to our working fluid because the working fluid is colder than the outside air or the groundwater. That is brought back here. That fluid carries energy with it, and then the compressor does work to make the temperature higher than the room temperature, and we have moved energy from the outside to the inside and multiplied. The numbers turn out to multiply the energy that goes into Q sub H. In a real heat engine, of course, we're going to lose some of our work. It doesn't get to the inside of the house. So we're not going to worry about that in my class. Talk to your instructor on whether you need to concern yourself with this or not. Another illustration here of what's happening. We have outside air perhaps at minus 5 degrees Celsius, and then we want to take energy from that air and move it into the house. So the working mechanism picks up the energy from the outside air, and then using the compressor makes the working fluid of the heat pump at a higher temperature than the inside of the house, and energy is delivered to the inside. We've moved energy from the outside to the inside is an important feature here. We have to pay for the work done to run the heat pump, but the energy here is free. The energy in the air or the energy in the groundwater that we're picking up, we do not have to burn a fuel to create this energy. It exists in the air, it exists in the groundwater, and we'll get to that discussion shortly. So here's a drawing of a heat pump. Can run both ways depending on which way the fluid goes around the circuit. My class is not going to concern itself with that, but let's take a look at a calculation. So we have this definition. It's kind of the equivalent to the efficiency of a heat engine, but coefficient of performance for a heat pump, CP, coefficient of performance. We can measure how effective a heat pump is by taking a ratio here of the energy that reaches the high temperature region, the inside of the room, for the case of a heat pump delivering energy to a house. So Q sub H, the energy that comes into the house, divided by our work number that goes into the heat pump. Q sub H divided by W. For a Carnot heat pump, our best coefficient of performance can be calculated using temperatures. So T sub H, the high temperature inside the house, and then the difference of temperatures between inside the house and outside. Notice these are single T's, so in doing this calculation you must use Kelvin, don't use degrees Celsius. When will the coefficient of performance be high? When will we be getting a lot of energy moved into the house compared to the work done? When will the coefficient of performance be high? Well, if we have a small difference in temperature, so if we're not in the very coldest months, where there's a big temperature difference between the inside and the outside of the house, it's difficult to move energy from the cold reservoir to the hot reservoir when there's a big temperature difference between the two regions. We get our best result when TH is not too much different than TC, and we get our best delivery of energy inside the house. If you're using a groundwater system, then you don't have to worry quite so much. The air temperature is very variable through the winter months. A groundwater system, this T sub C is more reliable and a steady value and not as cold as the air because it's still liquid water. It's not below 0 Celsius. Oh, let's suppose we're in Nebraska and running a heat pump, and let's suppose on a particular day the air temperature in the inside the house thermostat setting caused CP to be 6. We use $10 of electricity, and maybe not in a day, maybe in a couple days, but we use $10 worth of electricity for the heat pump. What's the value of the energy delivered to the home? So I'm doing this calculation with dollars instead of joules, and that's fine. So if we have CP is 6, and we use $10 worth of energy for W, what's the value of Q sub H? Well, that's not too bad. 6 here, $10 here, $60 for Q sub H. I use $10 of energy in the heat pump. I get $60 of energy delivered to the house. And again, assuming no losses, an ideal engine, ideal heat pump. So CP is 6, $10 for the W, $60 for Q sub H. How much of this energy is free? $60 came into the house worth of energy. How much of that energy is free? Well, I had to pay $10 for the work. $50 is free. $50 is free. I spend 10, I get 50. There aren't too many businesses that run that way, but heat pumps do run that way. You put in a little bit of work, you get a lot of energy moved into the inside of the house. Well, so free energy, what's the source? I've already mentioned air or groundwater. Is air at minus 5 degrees Celsius, does it have energy? Air at minus 5 degrees Celsius? Well, yes. For a simple gas, the energy inside the material is 3/2 of the number of moles times the gas constant times the temperature, but not temperature in Celsius, temperature in Kelvin. So for at minus 5 Celsius, we've got 268 here to put in for the temperature in Kelvin. Minus 5 plus 273 to convert to Kelvin. So 268 for the Kelvin temperature. The outside air in winter does contain energy, and heat pumps can extract that energy and deliver it to a home. So that's the mechanism of the heat pump. For my class, I'm not going to go over the equations for the refrigerator. They change slightly in measuring the coefficient of performance for refrigerators. But just going to do the heat pump. That gives you the basic understanding. The heat pump is a device where you spend a little bit of energy to run the mechanism. You gather free energy from the cold reservoir, and then you deliver more energy than you pay for through the heat pump working process. We move free energy from the cold reservoir to the hot reservoir, and we get a value here. More energy is delivered than what we spend for. Now, heat pumps are expensive. The equipment is expensive to install, and depending on where you're located, roughly might take 10 years to get back your money in your investment. And then after the 10 years, your utility bills are smaller. They're smaller right away after you install the heat pump, but you've got this perhaps debt that you have to pay off for the heat pump equipment, or you lowered your savings account to pay the installation cost. After 10 years, roughly, you start putting money back into your savings account that you don't have to spend on the utility bills. You're making money. You're paying it off. You're breaking even after about 10 years of your savings on utilities, balancing off the cost of the initial investment. So, talk to your local heating contractor to get more details, but it's worth considering. So that's where we're going to end this particular video, and I hope you keep working problems and stay